All right, everyone, we're back for part two, which is going to be the hydration of alkynes. We have two reactions here to consider. So one of them is acid catalyzed hydration, where we're going to essentially see the equivalent of Markovnikov hydration to an alkyne. And then we'll look at hydroboration oxidation, which will give us the anti-Markovnikov equivalent for alkynes. Okay, so the first one we're going to look at is acid catalyzed hydration. Okay, so let me give you this reaction in terms of conditions, then we'll talk about some regioselectivity and then some mechanistic aspects. Okay, so again, in order to observe the regioselectivity with alkynes, we must use a terminal alkyne. So I'm going to use a terminal alkyne to think about the products of this reaction. All right, so notice here I have carbon 1, which is less substituted, and carbon 2, which is more substituted. Okay, and that will become important when we look at the products. So the reagents for this reaction are mercuric sulfate, HgSO4, sulfuric acid, H2SO4, and water, H2O. So in terms of reagents, this is kind of a hybrid of acid catalyzed hydration and oxymercuration reduction that we learned back in chapter 6. Okay, so mercury is going to be used to activate the alkyne to make it more electrophilic, and then we're going to see that water is used in a similar way as a nucleophile. Although we're not going to write the mechanism out of this reaction, we will consider some of the mechanistic intermediates that govern the formation of the product. Okay, so the products of this reaction. Okay, so if we were to think about this as an equivalent, reaction to the hydration of alkenes, we learned that we add, following Markovnikov's rule, we would add OH to the more substituted side and H to the less substituted side. Okay, so you could imagine, well, what if I did that twice? So I'd get a diol at the same carbon, so a gem diol. Okay, but it turns out that there is a mechanistic intermediate that we'll take a look at that is not particularly stable and prevents us from doing that reaction. So the product of this reaction is actually a carbonyl at the more substituted side, which hopefully, what do we recognize this functional group as? A ketone, right? Okay, so we're going to arrive at ketone products where we've oxidized, or not oxidized, but we've hydrated the more substituted position of the carbon-carbon triple bond. So in this case, carbon number 2. Okay, carbon number 1 ended up with 2 new bonds to hydrogen. Okay, so let's think about what some of the key mechanistic points are in terms of, how can I think about this reaction and why is it that I get to this ketone product? Okay, so let's just label this as mechanistic considerations. All right, and we're not going to look at the whole mechanism. We're just going to consider, what's governing the formation of the ketone product. Okay, so let's just imagine that we were to do this reaction. So we have mercuric sulfate, sulfuric acid, and H2O. Okay, so let's just go along the premise of adding one equivalent of water across the carbon-carbon triple bond following Markovnikov's rule. So I've added OH to the more substituted side and H to the less substituted side. Okay, so we can see our elements of water right here. Okay, so we've added water across the carbon-carbon triple bond following Markovnikov's rule. Okay, so this structure, okay, is not particularly stable. It is called an ene-all. Okay, so ene for the alkene, all for the alcohol. And it turns out that these enol species, in the presence of either acid or base, okay, so H plus or OH minus, so in this case we're in acidic conditions, okay, so this is really an intermediate of the reaction. So this enol, in the presence of acid or base, rapidly converts to the corresponding carbonyl species. Okay, so we basically have seen now when we form the enol, it's not particularly stable. We're in the presence of acid, and so this is an equilibrium process between the enol and this ketone that we've formed. This process has a name. It's called tautomerization. Okay, so I want to talk about this process, tautomerization, for a few minutes and think about how it relates to this reaction and the reaction we're about to learn, hydroboration. Okay, so tautomerization. We need to talk about that for a second. Tautomerization. Okay, so first, let me give you the definition of tautomers. You might have seen this on our isomer field guide, but now we're going to realize what it actually is. Okay, so tautomers are structural isomers. Okay, so remember, different atom connectivity, same molecular formula. They are structural isomers that differ in the position of one proton and one double bond. This is one example of tautomers. Okay, so up here, the enol and the ketone form, these were known as tautomers. So specifically the type of tautomerization that we are going to see in this reaction and the next reaction is called enol-keto or keto-enol tautomerization. Okay, so let me just talk about that again a little bit more. All right, so here's a generic enol. Okay, and this is an equilibrium process. Again, it can be catalyzed by either acid or base, where we arrive at the corresponding keto form. And we call this the keto form because it's not always a ketone. In this reaction that we're learning, it's a ketone, but it could also be an aldehyde. But what we're seeing is that the carbon that was bound to the OH in the enol ends up as a carbonyl. All right, and so let's think about then how this reaction or how this pair of tautomers fits that definition. Okay, so these again are related as tautomers. Okay, so we've moved the position of one hydrogen. Okay, so this hydrogen as part of the OH, that hydrogen's gone. It's over here at that carbon adjacent to the carbonyl. And then we can see the position of the double bonds changed. Here we have a carbon-carbon double bond, and here we have a carbon-oxygen double bond. So we can see how this fits the description. All right, so this reaction involves tautomerization because we form an enol under acidic conditions once we've added water across the carbon-carbon triple bond. Okay, and so what we need to know is that generally, okay, the keto form is more stable. And that arises because the carbon-oxygen double bond is a stronger bond than the carbon-carbon double bond. Okay, so since the keto form is more stable, it would be favored at equilibrium. Okay, and we're not going to talk about the mechanism of keto-enol or enol-keto tautomerization. That's something that you'll talk about to a lot of detail in Organic 2, because you'll think of other reactions that involve this process. You'll also learn in Organic 2, are there any situations where the enol form would be preferred? Okay, but for now, we're going to go under the assumption that the keto form, where we have a carbon-oxygen double bond, a carbonyl, is favored. And so that's going to be the overall product of these hydration reactions. Okay, so what I want to do now is just look at some examples of this hydration, acid catalyzed hydration of alkynes. Okay, so let's first look at an example of a terminal alkyne, and then we'll look at an example of an internal alkyne. All right, so we have our carbon 1 and carbon 2, more substituted and less substituted. So let's draw the enol intermediate. Okay, so think about adding water across the carbon-carbon double bond following Markovnikov's rule. So here's the enol that's formed, but the product that we actually arrive at then is the corresponding ketone at that more substituted position. So this is the product, PDT product observed. Okay, so it's useful for me to think about the enol, but that's not the product that you were going to draw, when you're predicting the products. The product of this reaction is the ketone, that one that I noted there by the product being observed. Okay, so lastly, let's go ahead and look at an example of an internal alkyne. Okay, and in this case, we have our 6-carbon chain and the alkynes between carbons 2 and 3. So notice how carbon 2 and 3 are not related through symmetry. So they're different, but they're similarly substituted. They both have one carbon-based substituent. So in the product then, I would arrive at 2 different products. Okay, so I could add the carbonyl at position 2. Okay, or I could, and I will, add the carbonyl at position 3. So again, for regioselective reactions of alkynes, we cannot observe the regioselectivity on an internal alkyne. So often we will get mixtures of products, okay, in terms of regioisomers or constitutional isomers. One exception to that would be, what if we had a symmetric internal alkyne? Like, for example, what if we had this alkyne? So now carbons 3 and 4 are indistinguishable from one another, because if I were to count the carbon chain in the other direction, I would see that, you know, I have the same molecule. I have an alkyne between positions 3 and 4. So both carbon 3 and carbon 4 have an ethyl group hanging off of it. So in this case, if I were to do a hydration reaction, I would only end up with one product. And it doesn't matter if you write the carbonyl at what we've shown as carbon 3 or carbon 4. Those are the same exact products. Okay, so we would only have the one product to consider. Okay, so let's count our carbons here. All right, so what you should think about then is, well, what if I drew the carbonyl at position 4? If you just rotated that molecule around, you'd have the same molecule we've drawn there. Okay, so this reaction, acid catalyzed hydration, is essentially the Markovnikov addition of hydration of alkynes. Okay, so the last thing that I want to consider then is the hydration of alkynes through an anti-Markovnikov model. So this is hydroboration oxidation. So we're still hydration of alkenes, or alkynes rather. And we're going to look at hydroboration oxidation. Okay, so here is the overall reaction. So again, I'm going to use a terminal alkyne so that I can see the regiochemistry. Okay, so we're going to have a new borane reagent. Okay, so what I want you to consider is that boron and its similarity to BH3. Okay, so it's a boron with 3 bonds. Okay, so SiA is a carbon-based substituent, which I'll give you the definition for here in a second. And we have THF as our solvent. Step 2 is the same as it was with alkenes, so H2O2 and NaOH. Okay, so we're again going to do a hydration reaction. Okay, so we also can consider this enol that would initially form in this reaction, where I've added water across the carbon-carbon triple bond, and I've added the OH to the less substituted position and H to the more substituted position. So think about anti-Markovnikov addition of water across the triple bond. But when we form this enol, as we talked about, enols are not particularly stable, right? And so we would rapidly tautomerize to the corresponding carbonyl species. But notice now how this corresponds, okay, at carbon 1 to an aldehyde. So for terminal alkynes, I will end up with an aldehyde under these conditions, where under acid catalyzed hydration, I ended up with a ketone. Okay, so let me define that reagent. Okay, so the reason why we use this reagent is because it enhances the regiochemistry or regioselectivity for anti-Markovnikov addition. All right, so let me give you its structure. So there's a BH bond. That's important because, that's where the chemistry is happening. And then here is the R groups. All right, so what does that stand for? So it's disec isoamyl borane. Okay, so this part is the SIA. We've abbreviated it as SIA for disec isoamyl borane. Okay, and again, the reactivity of this reagent comes from the BH bond, just like one of the boron hydrogen bonds in BH3 when we were hydrating an alkene through the anti-Markovnikov model. Okay, and so again, this enhances the regioselectivity to put the OH on the less substituted carbon of the enol, and then that tautomerizes to the corresponding aldehyde. Okay, so let's go ahead and look at an example of this reaction, and we'll just look at the first step of the mechanism to see the similarities between this and the previous reaction. All right, so let's use this alkyne. Okay, so again, our conditions are going to be our isoamyl borane, THF, and then H2O2 and NaOH. All right, so the products of this reaction we could consider. So we have a 4-carbon chain. Carbon 1 is the less and carbon 2 is the more substituted side of our alkyne. Okay, so the initial product coming out of this reaction then would be the enol, where the OH is at the less substituted position. Okay, so I've added OH, the less substituted position, H to the more substituted position to get to this enol. And then the products of this reaction, so remember keto-enol tautomerization can happen under acidic or basic conditions. We're under basic conditions in the oxidation step with NaOH, and so that catalyzes the tautomerization step. And now we would end up with this aldehyde. Okay, so we end up with a carbonyl at the less substituted side of our carbon-carbon triple bond. Okay, so let's look at just briefly the mechanism of the first step, the hydroboration step. And we'll see the same set of arrows as we did for alkenes. I just want to highlight the regiochemistry. Okay, so we're going to line up these isoamyl groups. Okay, so these two isoamyl groups are going to be away from the bulky R group. We do that to reduce steric strain in the transition state, just like we talked about for alkenes. So again, we're going to point these isoamyl groups away from the R group of the alkyne of our terminal alkyne. Okay, and that is what is determining the regiochemistry of this reaction. Okay, so now what follows is the same set of arrows we saw for alkenes. Okay, so the pi bond is going to attack the boron, the hydrogen, rather the bond between hydrogen and boron, that hydride with its electrons, are going to attack the more substituted position. Okay, and so this is going to give us the product of step one. Okay, where we've added H and B and boron across the carbon-carbon triple bond. Let's fill in everything else. And we can see this happens by syn addition, but you can rationalize it in the products. There is no stereochem to observe. And so we don't need to worry about stereochem necessarily in this step. Okay, but this would be the product of step one with diisoamyl borane. Okay, and then we could continue through that. Okay, so this step is really diisoamyl borane, and then this step would be our NaOH H2O2. And we're doing a similar thing as we did in the chapter 6 reaction, which is we were replacing the boron carbon bond or oxidizing that to a carbon oxygen bond, and then we'll recognize this as the enol, and we can do that tautomerization as we talked about to give us the product that we drew up above. Okay, so the last thing I want to do for this reaction is just look at an example. So we see one example with a terminal alkyne up above. Let's look at one example of an internal alkyne. Okay, so again, we'll have a similar issue as to what we did for our acid catalyzed hydration, which is if I have two carbons of our alkyne that are not related through symmetry, like in this case, okay, because on one side I have an ethyl, on the other side I have a propyl, I'm going to have to consider reaction at both of those positions. Okay, so in this case, both carbons 3 and carbons 4. Okay, so, and the other thing to note is, since this is an internal alkyne, this reaction, acid catalyzed hydration, would give me the same products, because again, we cannot observe the regioselectivity for internal alkynes. Okay, so if you have an internal alkyne and you're doing hydration, it doesn't matter which reagent that you use, either acid catalyzed hydration or hydroboration oxidation. Okay, so we'll have our 7-carbon chain. There it is. Let's go ahead and count our carbons. Okay, so I can add the carbonyl at position 3. That's one product. And then my other product would be the carbonyl at position 4. Okay, so in this case, I would get a mixture of regioisomers, or we could also call them constitutional isomers. All right, so lastly, just to reiterate, we have our two hydration reactions. We have acid catalyzed hydration, which gives us ketones for terminal alkynes, and then we have hydroboration oxidation, which gives us aldehydes for terminal alkynes. Internal alkynes are in those two reactions give you the same set of products because there is no observable regioselectivity for internal alkynes. Okay, so what we have left to do for this chapter is to look at the reductions. Okay, so there's going to be 3 varying reductions that we'll start class with on Friday, and then we have one general class of questions to consider, something called synthesis, wherein we're going to try to put together multiple reactions to, prepare a molecule of interest, and then we'll also start chapter 8 on Friday. Okay, so again, if you have any questions, please go to the discussion board in Canvas, ask them on Facebook, send me an email, come to office hours, and I'll see you guys, or I'll be talking to you guys all on Friday.